Okay, so how's it going? So today we are going to start talking about the wave nature of light and electronic structure. So this whole unit is going to be about electrons in the atom, where we can find them, how we can find them, and some other parts and other things that those behaviors cause. All right, and so with that, let's just jump right into it and get started, okay? And so first off, when you hear the phrase electronic structure, right up here, we're talking about the arrangement of the electrons in an atom. And so that's what it means. There's nothing else to it. That is how we talk about it and how we figure that out. So now, one of the weird things that we got to talk about when we talk about electrons is we have to talk about the electronic spectrum. And the reason for that is because a lot of light studies gave rise to what we know about electrons and where they are and how they are, and so that's how we use that. Okay, so that's kind of what we got to do. And so the first thing that we're going to talk about is the electromagnetic radiation. So electromagnetic radiation. I'm just going to write it over here because I made the space too small. So electromagnetic radiation. And so EMR is the term for it. It's all the 6 types of radiant energy, which are responsible for carrying radiant energy through space. The 6 types of these are gamma ray radiation, X-ray radiation, ultraviolet, visible, infrared, microwaves, and radio waves. So these ones are the gamma ray rays right here. Those are the most powerful, most energy, and then radio waves are the least energy. And so we can see that right here up in the graphic, up in your right hand side. You can see higher frequencies, lower frequencies to the right in this graph. Wavelength, you can see this is smaller wavelengths to longer wavelengths, and you can see the visible spectrum is blown up right in between here. And then these are the different wavelengths of those colored lights in nanometers. Okay. Now, all 6 of these types of radiations have some things in common. So first off, they all travel at the speed of light in a vacuum, c, which the number that we're going to use for that is 2.998 times 10 to the 8th meters per second. Okay, and that's always, it always travels that speed. So it is the speed of light in a vacuum, but that's the number we're going to use just because that's the number that we have, and that most of our calculations are going to involve that. The other thing that most waves, or most of the members of the electromagnetic spectrum have, is that they all have wave-like properties, and so they all have wave properties, which is why we can characterize everything that we're doing in terms of that wave-like properties. So, yeah. Now, because all these types of energy exhibit wave-like behaviors, we need to understand some basic wave terms. And so that's what this is. So here we are, frequency wave diagram. So this is a wave. These are crests, these are troughs. So the wave tops are called crests. The wave bottoms are called troughs. We actually measure what's called a wavelength. That is from either the top to top, the bottom to bottom. And so a wavelength is right here. Is the actual physical length of a wave measured from crest to crest or trough to trough or from the same point on the wave. It doesn't really matter. Okay, there are some common wavelength measurements. So we can measure angstroms. Uh-oh, I didn't want to move that. Sorry. We can measure in nanometers, and we can measure in micrometers, millimeters, centimeters, meters, or kilometers. So for our really, really short waves, our very, very high energy gamma rays, we might measure our wavelengths in angstroms because their wavelengths are super small, they're super fast, and they pack a whole lot of energy. If we're talking about a radio wave way over here, we might measure our wavelengths in terms of kilometers, which is going to be something entirely different. And so these are the conversions in meters. Unfortunately, here on my graphic, the exponents kind of got eaten. They got put down as subscripts, but those are exponents. So your copy of the worksheet actually has those in the right spot. So the PDF transformation process was not kind there. So, oh well. Now, The longer the wavelength, the less energy it has. So I already said that. So the longest wavelength radio waves have way less energy than our shorter wavelength gamma ray radiations, and those are way more energetic. So, and that's kind of how that plays out. So the next thing we got to talk about, and I'm going to erase some of these terms. Wow. Here we go. We're going to scroll this up so we have access to a little bit more of it again. All right, so now next thing we're going to talk about is our frequency, is the full number of waves. Okay, I see something funny just happened there. Frequency is, and they have N, so the PDF process was not kind to that. The frequency symbol is nu. It's kind of a funny V with a tail on it. Okay, and I just noticed it up here. The lambda, okay, so this isn't supposed to be an L. This is supposed to be the Greek letter lambda, which looks like this. So I'm sorry that that transferred weird, but that's what it did. So that is the Greek letter lambda. Okay, so frequency, nu, is the number of full waves that pass a given point in 1 second, measured in units called hertz or reciprocal seconds. So, so this whole waveform, so from this point to this point, that's a whole wave, and the number of those that go past a given point in a second is what we refer to as frequency. And so that's what that is. Okay, the more waves passing in a second, the higher the frequency. Nice job dropping the pen cap there, Matt. Okay. The higher the frequency, you can't even read that because the pen just died. Okay. Let's see if I can do it again. Higher the frequency, and the blank energy the wave generates. So that's the more energy the wave generates. More. There, now you can see it a little bit. Okay, so there we go. I'm going to pause for a second, erase these, we'll move on to the next page. Okay, so now what we're talking about here, and I'm going to bring this down here. Okay, so then this is the top of the next page. The next one that we talk about on our waveform is amplitude. And amplitude, there you can see that. And it's not squeaky. Look at that. Amplitude is the measure of the wave's height from the resting position, which was the orange dashed line in your graph. And so this is your orange dashed line. And if we have a waveform, that measurement from there to there, that's your amplitude. Okay, and that's just how high the waveform is. So that's what that is. Okay. Now, since all forms of electromagnetic travel at the same speed, which gives rise to a following equation. So here is your equation. Okay, and we're going to use this a fair bit. And so what we got, we say where lambda, so lambda times nu is going to equal the speed of light. And so lambda, cross the I out because it didn't transfer, is equal to the wavelength. N, well, it's not N, it's the funny V, is nu, and c is the speed of light. And remember, speed of light is 2.998 times 10 to the 8th meters per second. Okay, so we're just using that equation to figure out what's going down with this. So here's a sample problem, and this is pretty standard. This is how it's going to work. So I have a yellow light problem. It's 589 nanometers. What is its frequency? So first thing I want to do is you'll notice that my speed of light is in meters. And so my unit of nanometers for my wavelength isn't going to cut it because it's not the right unit. So I have to make sure that I do the calculation and fix that. And so let's start with that. So I'm going to start with my 589 nanometers over 1. Now from the page that I had before, we saw that every 1 meter has 1.0 times 10 to the 9 nanometers in it. So nanometers cancels. 589 divided by 1.0 times 10 to the 9 nanometers. That's going to give me 5.89 times 10 to the minus 7 meters. Okay. Now that's my wavelength. And so I have one of those numbers down. I'm trying to find the frequency. Okay. So I'm looking to find the frequency with this one. So I'm going to rearrange this guy. I'm going to do it over here so it's out of the way. So wavelength times frequency is equal to c. I want that by itself. So frequency is going to equal the speed of light divided by its wavelength. Okay, so that's the frequency, or the what I'm doing right here. And so my frequency is going to equal my speed of light, which is 2.998 times 10 to the 8 meters per second, divided by this number, the 5.89, times 10 to the minus 7 meters. So I plug that into my calculator. I want you to pay attention to the exponent and the exponent. Okay, so we have an exponent of an 8 divided by an exponent of a negative 7. When you do the math on it, remember you're subtracting it, and so we're minusing a negative, so we're adding a positive. And because we're dividing it, so the order of magnitude here, you're going to get something to the 14th power or the 15th power, depending on the number. So just be cautious for that and watch for that, because that's something that makes people make mistakes. So the number that I got was 5.09 times 10 to the 14th hertz, which is the frequency unit, or if you prefer, you could write seconds to the negative 1 power. Okay, and that is the other unit for frequency. So that's all I got on this one. So we'll give that one a stop, and we'll talk to you about it in a little bit. Okay, bye.